In example 2, we're going to be taking a look at trying to justify that a limit does not exist. And we have a new limit here, very similar to kind of what we had back in the first example. Now, one of the things that we talked about back in example 1 was that we had to think about the different paths that we were going to approach our limit point from. So in this case, we're approaching 0, 0. And so what we need to come up with are some different possible paths that we could try to use to approach 0, 0. Remember here that when I'm drawing my x and y axes, this is really to help try to simplify kind of this more complicated picture that we have occurring in 3 space. Remember that in 3 space, we have some sort of a surface, okay, that's kind of floating here up above the xy plane, at least in this picture. And we're going to be interested in trying to figure out what z coordinate this function is headed towards as we move kind of towards the point down in the xy plane that may or may not correspond to a point up on that actual surface. So when we think about our paths, these paths again are going to be moving across this particular landscape, and we can come up with all sorts of different paths that might lead us towards this particular point. And when we kind of draw these paths down in the xy plane, maybe we get some sort of weird shape, kind of like the ones that I'm drawing here, or maybe I get very, very simple shapes. But to kind of make this picture look cleaner, to understand what are the xy paths that we're taking, we often attempt to try to draw them in kind of just our standard xy coordinate system. I'm going to highlight 0, 0 here since that's the point that I'm going to be trying to approach. And now I'm going to try to think about 2 paths that I might be able to at least start with. Okay, so maybe some easy paths that I could possibly choose would be like the x-axis. That's a perfectly reasonable path. It's a very simple path given by y equals 0 that would lead me right through the origin. So let's kind of see what's going to happen if I move along the surface along that particular path or in that sort of direction. Okay. So I'll state here that if we move along y equals 0, which again is my red path, then I can start to see what's going to happen to my limit. My limit here, which is approaching 0, 0, x y to the third over x squared plus y to the sixth. That's going to simplify up here a little bit, because if y is again always going to be 0 on this entire path here, then I can really just replace all y's with zeros. And that's going to allow me to really simplify up what I'm taking the limit of. So it'd be x squared plus 0 to the sixth. So notice here I've kind of reduced this down to a limit where I just have x going towards 0. And I'm going to have 0 in the numerator and x squared in the denominator. And this is going to simplify up again. I'm just going to really have 0 here. Remember, I can simplify the inside before I complete the limit. And then the limit of 0 here is 0. Okay, so if we move along the path of y equals 0, we get a limit value of 0. Now, if we're trying to show the limit doesn't exist, we're hoping to get a different answer for the limit as we move along a different path. Now, again, there's lots of paths that we could choose that maybe move through x equals 0, y equals 0, this point, the origin, right? There's a lot of paths that go through that origin. One path that you might even think about is something like the path x equals 0. Okay. So the path x equals 0 would be going down this y-axis. Let's call that my green path right now. But one thing that I might notice about this is I'm going to get a pretty similar sort of result. So I'll write here, if we move along x equals 0, my green path, then I'll just write here, our limit becomes, and I can kind of see immediately what I'm going to end up with here. I'm going to get 0 for the x, but y for everything else. And what that's going to change in my problem is really just kind of what variable is going to have the 0. So I'm going to end up still with 0 ultimately in the numerator, because I'm going to get 0 times y to the third power. And then I'm just going to get a 0 squared plus a y to the sixth. But ultimately, if I go through all that work, I'm still going to get 0 over something, and so I'm going to end up with the final value of 0. So I still haven't been able to show that the limit doesn't exist. Now, the reason that I showed you here another path that didn't end up helping us is because that's going to happen to you all the time. You shouldn't ever be concerned that you've tried a second path and you got the same answer. That's going to happen all the time. What we have to come up with is other possible paths that might be able to work. Take just a quick moment here. Could you think of any other possible paths that we could use that would take us through the point 0, 0? And again, I try to stress to keep paths as simple as you possibly can, so hopefully your limit is as simple as you might be able to make it. All right, well, I mean, again, there's a lot of different possible paths you could choose, but maybe you could think of a path like this one, a path that runs right along y equals x. Although, you know, a linear path is easy, but of course there's lots of linear paths. Like you could have also chosen a path maybe like y equals negative x. Or actually, you could have almost imagined choosing like any linear path that had like any different possible slope you could imagine. I'm going to kind of really clutter up the picture here by imagining all sorts of different lines that I could have chosen just with different slopes. And so actually, I'm going to do something really cool. I'm going to check all of these blue paths at once. So I'm going to say if we move along a path of y equals m times x, where m is going to represent the slope of this line. And I don't know what it is, so I just leave a placeholder in there. And then, of course, my y-intercept here is 0, so I just have a plus 0 at the back. But notice this represents every possible blue path at once. Well, in this scenario, our limit is going to become a limit where x comma m times x is going to be approaching 0, 0. Again, notice all I've done is I've just swapped out what y was equal to, and I'll do the exact same thing in for all the y's in the original limit. So here I'm going to have m times x to the third in the numerator, and then I'll also have x squared plus an m times an x to the sixth. All right, if I simplify this limit up, again, I'm still just going to be kind of down here to a limit where x is just approaching 0. Remember, m is just a placeholder for some number. And so in the numerator here, I'm going to have, let's see, I'd have like m to the third times x to the fourth when I simplify that out. And in the denominator, I'm just going to have x squared plus, let's see, that's m to the sixth times x to the sixth. Okay, so there's a little bit of work here that I'm going to have to do to try to figure out what this limit is actually going to equal. Oh, here's a quick little trick that I could do, because right now, notice that my limit is kind of producing 0 on top, but also 0 on bottom. And I could right now go ahead and choose to multiply here by a fancy version of the number 1. This is a classic trick that you might have done back in a calculus class, right? Like a Calc 1 course. I'm going to divide here by a 1 over an x squared and see how that changes the limit. Notice that if I was to do this, I end up with m to the third times x squared in the numerator. In the denominator, I have to distribute this and divide both of the pieces. So I'm going to get 1 plus m to the sixth over x to the fourth. But now it's really easy to figure out what this limit's going to be. If x is approaching 0, I'm going to end up with 0 in the numerator and 1 plus 0 in the denominator. Ah, shoot. Again, I end up with a result of 0. Okay, so this is, wait a minute, this is weird. I've checked one path initially, I checked a second path, And now I just checked infinitely many extra paths, and all of those paths have a limit of 0. Doesn't that mean that the limit's 0? Like, we said this last time in the previous examples and previous theorems that we talked about, is that, well, if the limit is going to exist, it has to be the same value across all possible paths. Didn't I just check all possible paths? Like, I checked all directions. Well, close, but not quite. Remember that I have to consider all possible functions that could lead me to 0, 0. So there's lots of functions here that I left out. Functions like y equals x squared, or y equals x to the third, or y equals x to the fourth, or y equals x to the fifth. Like, all of those are other paths that I could also use. But I could even use even more gross paths, like y equals the sine of x. That would take me through 0, 0. So even though I've checked infinitely many paths now, and they've all come out the same, I still can't say that the limit here is 0. So this is where sometimes people can get a little frustrated, right? Because they're like, I've checked so many paths, Kyle. What other path could I possibly take? Well, a lot of this is going to come down to some trial and error and thinking about what you might be able to say sub in for y to make things as simple as possible. Right now, one of the things that's kind of annoying is that in our denominator of the fraction, we have two different powers. And so we can never really combine what we have down here. They're not like terms, even if we replace y with stuff with x. Well, what I'm going to go ahead and do here is maybe try to replace y or replace x with something that will allow those denominator values to have the same power, and then maybe be able to be added up. So I'm going to take a brand new path. I'm going to take a path that looks like this. How about a path x equals y to the third? Or that's the same as y equals the cube root of x. Now, if I was to go ahead and try to draw this here in the picture, let's see, the cube root of x. That's going to be something that looks kind of like this. Right, so here's a path that I'm taking as I move towards 0, 0. This is my orange path. Well, in this case, notice what's going to happen again with the limit. I have a limit of, at this point, I'm going to replace x with a y to the third, and I'm still going to have y, and that's going to approach 0, 0. And then that means that in here I'm going to have a y to the third times y to the third for the numerator. In the denominator, I'm going to have y to the third being squared plus a y to the sixth. If I simplify this up, notice what I'm going to end up with here. Still have my y to the third y moving towards 0, 0. But in the limit, on the top, I have y to the third times y to the third, so that's y to the sixth. And in the denominator now, notice I'm going to get a y to the sixth plus another y to the sixth, and I get 2y to the sixth. Well, if I could now cancel out those 2y to the sixths, I'm going to be left with a limit of just 1/2. And the limit of just 1/2 is going to be 1/2. You could have gotten a very similar result if instead of doing x equals y to the third, you did y equals cube root of x. You get the same basic results popping back out. I just did it this way so I didn't have to write the radicals. But notice here, I do indeed get a different value of 1/2. So I can make the statement that since the limit is not the same along all possible paths, to 0, 0, the limit does not exist. So dealing with these new paths is really the key. You need to, when you're going through your problems, really be thinking about different possible paths that can approach your specific point. Again, the number one way that people get questions like this wrong is by just never thinking about paths. They try to do something completely different and they always end up getting a wrong answer, or at least an answer that's completely unjustified. Also, though, when you're doing this problem, don't be surprised again if you try over and over and over again and keep getting the same answers. Sometimes you're going to have to try to think outside the box, think about what maybe you would like to have happen with the particular expression that you're taking the limit of, and come up with a function that might help you simplify things in a nice way.